So welcome back. Let us start the rest of the session. We will have Monica Orienti speaking about radio jets and Seyfert galaxies with VLBI and FERMI.
Okay. Sir? No. It should be closer. Even closer?
Yeah, test it.
Can you hear me?
Yeah.
Okay, thank you. Okay, so I'm going to talk about radio jets in Seyfert galaxies from a radio, VLBI, and a FERMI gamma ray point of view. I will present works made by collaborators and other people, so I try and make a review of this talk. The outline is, first of all, an introduction on radio loud and radio quiet. Radio loud, just to make a connection with all the talks we heard this morning, and then I will show differences with the radio quiet AGN. Then I'll move on the gamma ray emission, and then I go straight to the radio and parsec scale emission from the Seyfert cores that are pretty the brightest part, and then some future perspective. So let's move a step back. So again, to the radio loud part. So as we heard, these guys are roughly 10% of the AGN. They are powerful in the radio, and the main ingredient is the presence of a relativistic jet. So relativistic particles, magnetic field energy is produced in the central part, in the core. It's channeled through jets interacting with the interstellar medium or intracluster medium, depending on the sizes of these objects, reaccelerated. So the main ingredient is that the energy in the spectral energy distribution broadband is non-thermal radiation from the jet. And as you see, they are pretty powerful. The luminosity, this is 1.4 gigahertz, for example, is higher than 10 to the 23. The size is from parsec scale, so entirely within the host galaxy, but they can reach megaparsec scale. So they have a huge range of sizes. They are hosted, like you can see here. These are totally within the host galaxy or even within the narrow line region of the host galaxy. They usually are hosted in ellipticals and quasars. And these are the ingredients. So relativistic particles, magnetic fields. So you have the synchrotron emission that you see in the radio. And the relativistic particles may scatter, interact with the seed photons, that they may be the same photons produced by synchrotron, or interact with seed photons like those at the torus or from the disk or whatever. But anyway, they can produce inverse Compton emission at the high energy. So these are the radio and the gamma ray part, let's say, or as you see these a few talks before, the double hump of the spectral energy distribution of the Blazar sequence. As I said before, only 10, 15 up to 20, depending on the authors, of AGN are radio loud. In the gamma rays, the extragalactic gamma ray sky is dominated by extragalactic radio loud AGN. So 58% of the 3FGL sources are extragalactic sources, and among these, more than 99% are radio loud AGN. So these are, well, the main difference from the 3FGL, the different sources. And so, again, as it was in the egret era, also now with FERMI, the radio loud AGN dominates the gamma ray sky. But as I said, they are 10, 15, 20% of the AGN population. And what about the majority of the AGN, the radio quiet? Well, the spectral energy distribution in this case is dominated by thermal emission, is related to the accretion-disk. And the majority of AGN are, as I said, radio quiet. So their radio emission is not so bright. It's not, it's not so bright. But it doesn't mean that they are radio silent. Absolutely, they are the dominant AGN population when we go to deep flux density. As we increase the sensitivity, the population of radio quiet AGN increases and dominates over the radio loud. So understanding the mechanism, the nature of these objects, it would be very important even if we think about the next generation of the SKA and the precursor that are now are built and started building in across the world. So understanding the differences between these two populations would provide important information for the physics that we will do in the near future. And the best would be in the radio, where they are more different, as well as in gamma rays, as you'll see. And as I said, they are not radio silent. They have some emission. However, the size is usually sub-kiloparsec scale, so their radio emission doesn't exceed the host galaxy. So they are not able to form this 100 of kiloparsec of megaparsec scale that we are used to see in FR1, FR2 galaxies. They are hosted in spiral, star-forming, or lenticular. They have a variety of radio morphology, like here. They may be unresolved, a little bit resolved. They may have extended emission or even structures that are similar to FR2 objects. And in many of these guys, there is a misalignment between the parsec scale and the kiloparsec scale structure. The interesting part is what's the origin of the nuclear emission from these sources? Is it thermal emission even in the radio? Is it from AGN, wind, hot corona? Or is it due to an ADAF, a low efficiency mechanism at the origin, like ADAF, ADIOS, and many other things? Or is there a non-thermal jet emission as well, similar, but much with less power than in what we are used to with the radio loud AGN? Or is it a combination of different mechanisms? The first problem, the majority of these objects are hosted in late type galaxies. So this means that there is a lot of gas, many stars, a lot of star formation. And as you can see here, this is a very famous Seyfert galaxy. This is the Galaxy, the UV. This is the MVSS. So you have all these radios coming from the galaxy and not from the AGN. This is a fantastic star-forming ring, nuclear star-forming ring. The scale is, this is just 1 arcsecond. And here, just here, a very faint core. So if we want to study the nature of the core emission, we must get rid of all this contamination. So another point is that large fraction from the radio emission we have is from stellar-related processes, as this is an interesting work by Thien et al., where they studied the infrared versus the radio, and they have a similar trend, a tight connection like between the radio and the far-infrared, like that found in normal spirals. And if we study the luminosity evolution, these are the radio loud, the radio quiet, and the star-forming galaxies. The radio quiet behaves similar to the star-forming galaxies. And if we have a look with the VLBI, so here we have, again, the infrared, and here we have just the flux density from the central part. This correlation is not present anymore. So there must be something that we need to understand, to find out what's going on. So it's not just star formation in this part, so we have to investigate a little more. Let's start with the high energy emission, so from the FERMI. This is a work made by Ackermann et al. In 2012. They studied 120 hard X-ray selected Seyfert galaxy without a strong starburst. So they were pretty sure that the gamma ray emission that may be detected is not, shouldn't be related to the star formation. And here there is the X-ray versus the gamma ray, the far infrared and the radio against the gamma ray. And they got just only upper limits. And as a comparison, here there are other star-forming galaxies detected in gamma rays, just for a comparison. And there were two possible claims and about on this 120 possible exception. So there were these two guys. However, having a better look at the data, this was a misassociated object, so it was ruled out. And also NGC 6814 was not confirmed in the 3FGL. So increasing the number of Fermi data, these two sources could not be, actually this was rejected and this was not supported. But, so this means that if there is some gamma ray from this object, it must be very low. So 10%, 1%, or even lower, depending on the sensitivity on the tight upper limits that you can get with respect to the X-ray emission. So Seyferts are not prominent gamma rays. But then there is Circinus. This was a dedicated study, and it was an analysis of 4 years of Fermi data, and they pointed out an excess in the correspondence of Circinus. And it's a point-like detection, and it's well fitted with a power law. These are the flux density and the photon index. This is similar to the photon index obtained for star-forming objects in star-forming regions. And the luminosity is something 10 to the 40s erg per second. That is 5, 6 times higher than what is expected in star-forming galaxies. So there is an excess. If we consider this is the infrared versus the gamma ray and the radio versus the gamma ray. And these are the star-forming galaxies. And these are the expected values if we consider that the gamma rays is produced by cosmic ray in the interstellar medium. Circinus is above it. So it is not consistent with only star formation. There should be something more. And possible scenarios, it was that one possibility is the inverse Compton in the lobes, because as you see in this picture, if you don't know Circinus, it has extended lobes on kiloparsec scale that may be the place of production of gamma rays. And another possibility is about cosmic ray protons associated with the lobes. However, this is to explain this, you must be too far away from the equipartition. Okay, there's some deviation from the equipartition has been found, but this would be too much, an order of magnitude, if I remember correctly. And in this case, the mechanism is highly inefficient. So they cannot be completely ruled out, but we need some more study to find conclusive results. So this is what we know so far in the gamma rays. Let's move back to the radio. And what do we need to understand, to study in detail these objects? Well, first of all, I think I convinced you, we need a high angular resolution because we want to get rid of the contamination from star-forming galaxies. So we want to have enough resolution just to go into the very innermost central part of the object. High sensitivity because these objects are faint. And so we must go at the microjansky level, or if it's possible, even lower. And polarization, because if we find a polarized emission, a synchrotron is non-thermal, should be. So we can, let's say, get rid of thermal from hot winds, hot corona. And we can also study resolved regions with well-ordered magnetic field. And a continuous frequency coverage that will allow us to study the spectrum and then to, again, helping us in disentangling thermal and non-thermal emission, as I will explain you in a while. So the role of VLBI. So far, there are many studies of Seyfert samples made with the VLBI networks of samples or individual objects. Here there is just a list of a few of the main papers I found particularly significant. And the parsec scale radio emission is almost ubiquitous in Seyfert nuclei. In almost every Seyfert, when you look with the VLBI, you pick up something. It can be a variety of morphology, like in the more extended structure, so unresolved, resolved, patchy, core jet. So it's not just one morphology always, but you have a variety of it. And another important, I think, point is that the VLBI picks up 100% up to just a few percent of the unresolved sub-arc-second resolution component you find. So it means that in some objects that they are unresolved with the VLA, let's say, you look at them with the VLBI and you find exactly the same flux density. In the majority of the other sources, you look with the VLBI and you have just a few percent or nothing, absolutely nothing. And this may be due to the presence of extended structures, but which are not so extended to be resolved with the sub-arc-second resolution, but they are too extended to be picked up by the shortest baseline of the VLBI network. So this is an example. This is a VLA observation with high resolution of this object. When you look at it with the VLBA, it's resolved into components and you cannot pick up more than 20% of the flux. If you add the VLA at the VLBA network, so you have a shorter baseline, this is the result. You have like an FR1 source. So you pick up much more flux density. So this is a pretty new work by Doi and collaborators that I found pretty interesting. Just to show you that, okay, you have these compact unresolved components, but then there is a lot of missing flux. And this is an example of how this missing flux is distributed. And another point, it may depend on the spectral index of the core. So there are Seyfert nuclei unresolved with the VLA with a steep spectrum. And these guys tend to lose more flux on parsec scale, while the flat spectrum nuclei may, in those galaxies, you may find all the flux density at VLBA scale. But this doesn't happen all the time. So you have always exception. In this case, this is NGC 4138, an example. You look at the VLA scale, it's inverted spectrum in the convention I used in this talk. And when you look at it in the EVN, you have the same flux density. So you don't lose anything. It's all the scale of the flux density of the emission is this one. And within the errors, even the spectral index match. And here is another example of this guy. This is a little bit extended, but even if you consider just the unresolved part, it's a steep spectrum. If you look at the VLBI, this is EVN actually, you have a compact core and extended structure. The compact core is, flattish with respect to this one that is pretty steep. There may be some imaging problem about the UV coverage, so don't consider that this is actually a spectral index of 2, but anyway, the meaning of this picture is that here you have a steep spectral emission. And in this case, you cannot get more than 15% of the flux density. So what's the nature of this missing flux? Priet et al. Selected a sample of Seyfert nuclei, almost all steep spectrum, and they could get just 20 or 50% of the total flux density. And so what we did in this, we considered the extended part of the emission that we miss, let's say for observational limitation. We made a computation assuming that this is free. And what we got is that in a radius of, let's say, 50 parsec, in the case of this object, the gas density would have been too high. That would have completely absorbed the emission coming from the nucleus, but that actually we see. So what they suggested is that the extended emission is not thermal, but it's non-thermal. And it's also supported by other observations like this one and of another object, that if you add a short baseline to the EVN, you can pick up extended steep spectrum emission. So that is difficult to explain steep spectrum emission with thermal. And what about the core emission? If we get rid of the production of the jet, if it is a sub-relativistic jet or whatever, we still have the problem of what is the main mechanism at the center? What's the engine here? So this is the famous NGC 1068. This is the location of the core. This is the brightness temperature at 5 gigahertz. It's considered pretty low to be consistent with synchrotron self-absorption. The spectrum is highly inverted. And the authors, Gallimore et al., suggested that in this case, the engine is producing thermal emission from the AGN wind and corona. This is another case. This is a new work we are doing on a sample of spiral galaxies with AGNs. And these are JVLA data instead of VLBI, but we improved the sensitivity a lot. And this is not a Seyfert, this is a liner, an SO liner nucleus. And we detected the polarization at the center with a 0.2%. So we observed a lot of this object. We went very deep. And we could find the polarization. So in this case, we can exclude that is like an NGC 1068, the thermal emission from the wind. But we suggest that here we are looking at a non-thermal synchrotron emission from a radio core that is not as bright as in the radio loud objects, but it may be similar to that, or it may be even, it can be interpreted also in assuming an adios scenario. So deeper observations and moving to VLBA when it will be feasible to reach such a sensitivity with polarization. So the last part is why we need a broadband coverage. This is what we have usually so far, before JVLA, let's say. that you observe at fixed frequencies. And in this case, you would say just a flat spectrum. It may be thermal, it may be the overposition of non-thermal synchrotron self-absorbed components. But when you look with the JVLA that you have, and SKA, I guess, in the future, you have roughly a lot of information here. And you can find out the convex of the spectrum, you can find out the peak of the spectrum. And from the peak of the spectrum, assuming synchrotron self-absorption, you can determine the magnetic field. And from the magnetic field, if it's too high, you may exclude that it's SSA. Like in this case, these authors made this homework, and what they got is that if the peak is due to SSA, the magnetic field in that Seyfert nucleus would be more than 10 to the 9 Gauss. So they excluded it. They made the same computation for the thermal emission, and so they computed the density of the gas around, and they found a value similar to what was found for NGC 1068 by Gallimore et al. So we have a zoology of things. So we cannot say that all the Seyfert galaxies have a thermal core, non-thermal core. So it's something pretty complicated. So my conclusion is that we know that radio quiet represent a large majority of the AGN population, and they will be more and more important with the coming up of the SKA and its precursors. And unfortunately, the AGN emission is contaminated by the stellar-related processes, so we must get rid of it if we want to understand the nature. The Seyfert are not strong gamma ray emitters. Thermal and non-thermal nature of the radio emission from the Seyfert is still not completely established. Some Seyfert may be able to produce a jet-like structure like those I showed you with Steve spectrum, but some Seyfert don't. And in the future, so to disentangle the contribution of star formation, just go to sub-second resolution with broadband observation, deep sensitivity, and polarization information. SKA, with the addition of VLBI, will be a step forward in our understanding of these objects. Thank you.
Thank you. Questions? Taban.
I'm just curious, maybe I'm missing something. In the Ackerman paper, why were they looking at hard X-ray? Because so they were looking at a sample, Seyfert sample, selected by hard X-rays. Mm-hmm. So that's done if you want to do a equal, a non-preferred sample of Seyfert 1 or Seyfert 2, because Seyfert 2 also pass, hard X-ray will pass through the torus, etc. But in this case, since you are trying to find jets or gamma rays from jets,
yeah.
Shouldn't one look for like broadline objects, because you want to look, perpendicular to the disk?
Yes. Well, I don't remember actually how the 120 sources were selected, so I should read again the paper.
Okay.
But it would not rule out such objects. Selecting.
No, it won't rule out, but you are just
included.
You are taking half of the objects which you already know that they will not have a gamma rays.
Yeah, perhaps. Virish?
Yeah, so it looks to me that if you look at the spectral properties and missing flux, I'm here.
Sorry.
Yeah. So if you look at the spectral properties and missing flux, so it seems that among the Seyfert galaxies, there are two populations. One is the flat spectrum where you don't see missing flux. Another is a steep spectrum where you see the missing flux. So is there any kind of fundamental difference,
No.
it's like X-ray properties or, accretion rate or something like that?
No, we couldn't find any. And some flat spectrum have missing flux. So there is not a very tight difference between these. There may be flat spectrum Seyfert nuclei with missing flux.
Okay.
And even considering Seyfert 1 or Seyfert 2, we don't find any difference.
Sasha?
How does it relate to radio-loud, radio-quiet dichotomy? If a radio-quiet galaxy is an FR1-like looking galaxy, but on a scale of what is usually called a core, then what makes it so small? And presumably a very low power, right? Is there any clues?
No clues. No understanding from.
Is there like higher density outside? So maybe the jet.
That may be one of the explanation suggested that the dense interstellar medium prevents the growth of the radio emission, but it's just one.
Yeah. Hello. Following up on that question, so if you have a dense medium around the system, and if you have optical observations, you will actually see emission in shock-excited gas. So is there any signatures in any of your samples which have tentative jet, small jets, low-powered, but shock-excited oxygen lines, O3 lines or something like that?
I am not aware of such works. I don't know.
Yes, there are. There are Seyferts that show evidence for driving shocks into the medium in various in optical emission lines and in X-rays. For example, I am speaking into the microphone, but I may not be holding it quite as close to my mouth as some people are. Let's try again. Yes, there is evidence for Seyferts driving small scale shocks into the medium, both in the X-ray and in optical emission lines. So the nearest Seyfert, Circinus, is an excellent example of this. We did some work on that in the X-ray some years ago. That wasn't what I was going to say, but since I'm holding the microphone, I thought I'd answer that question. Following up on Sasha's question again, where does this leave the radio-loud, radio-quiet dichotomy? It depends whether you think there is a radio-loud, radio-quiet dichotomy. What we know about the jets in Seyferts is that they're compared to the radio galaxies, the jet kinetic power must be very much lower than the radiative power. And again, we can estimate the jet kinetic power directly by looking at the impact on the external medium in those sources where we see it. So we know that, unlike radio galaxies where you can have the kinetic power and the radiative power being more or less equal, in Seyferts, it might be 1% or 0.1% of the radiative power. So your jet generation model has to be able to accommodate a very wide range of jet power to accretion power ratios.
Any other questions? Yeah, Marshmi?
I have a question. What would be the difference between the outflows and the jets that you would expect in these objects? How would you distinguish?
Difficult question. If it's thermal, perhaps the spectrum. If it's non-thermal, is it subrelativistic, synchrotron, cyclotron? Good question.
Yeah, Tony.
Yeah, I was just interested in the case where you were looking for the cause of that synchrotron self-absorption and you got 10 to the 11 Gauss. Can't you get over that? I mean, what was the structure of that source?
Unresolved.
So can't you get over that?
I think this one.
Yeah.
In this paper, it was undetected. Well, in this case, I just put just an example. The one where we did the homework, let's say.
And that one, I mean, can't you get over that by just assuming a much smaller angular size or something like that?
Oh, no, in this case, it's just an example, just what we can do with a broadband. Okay. This is actually another kind of object. It's an HFP object, and it's a VLA, so I don't know the resolution of the VLBI. So the other one I did, it's this source and
what are your scale?
In this one, it was the beam at the 5 gigahertz with the VLBI, with EVN, so a few parsec.
Okay, let's thank Monica again.